Alright guys, welcome back. This is again your instructor Mr. K, Code B. So I'm going to be discussing three-phase transformers today, and I'm going to go over delta and Y or star configurations. Okay, and then hopefully we'll be done with these. As I stated yesterday in my previous video, that this kind of configuration or delta and star configurations should be in Article 300 of your mic hold. But before I start with the delta and Y configuration, I like to refresh your memory regarding single phase and three phase voltages. And I'm going to draw something I already did actually up here, and I'm going to go over that difference between these two. So let's start off with single phase. Now these are called phasor diagrams. Phasor, P-H-A-S-O-R diagrams. They basically illustrate how things are connected and with one another. So when it comes to single phase, everybody knows that either we're going to have a two-wire single phase or we'll have three-wire single phase. But we have XY coordinate. This one is x-axis and this one is y-axis. So if you want to understand or draw single phase, the voltage or the magnitude, okay, is for single phase, it is on x-axis. There is no phase shift over here. So V equal to Vm, which is the magnitude, okay, at an angle of 0 degree, because when it comes to single phase, whether it's two-wire or three-wire, there is no phase shift between these two. So that's why the magnitude is going to fall on x-axis, which is reference point. But most of the time when it comes to single phase, whether it's a phase A or phase B, we do not actually show an angle, okay. But in reality there is an angle, but as far as single phase is concerned, there is no phase shift, so that's why we don't really show anything. So this is just brief review that when it comes to single phase, we get if we have two wires, because definitely we have a heart and we have to go back, and that's the return path. But one example, if you go back to voltage drops, that's equal to 2 times L times I times R over 1000. So in this case, this 2 is actually 2 conductors round trip. So this is your hot wire, whether it's A or B, phase A or B, doesn't matter. That stays on reference line on x-axis. Okay, and of course there is, if you remember, inductors and capacitors from AC/DC class, and if you compare voltage with current across inductor or capacitor, there is going to be a phase shift between those two. But I'm generally speaking voltage levels. Okay, so in this case there is no phase shift between phases across a single phase, whether it's just a single phase, two-wire single phase, or three-wire single phase. So always stays on the reference line. So that's why V is the same as the total voltage, or we can say angle of 0 degree, because that's on reference point. There is no phase shift here. But when you start moving up, now if you compare voltage with the current, of course there is going to be a phase shift. But that's why we use 2 right here. So this is your hot wire. Of course we don't show neutral in this case. Now as opposed to the single phase, now we got the three-phase phasor diagram. Again, you don't have to worry too much about that one, but if you just want to know where this one, just to refresh your memory, when we calculate three-phase voltages, three-phase currents, or voltage drops for three-phase, then what we do, we multiply everything by square root 3. So this is just to show you where square root 3 is coming from. Okay, so don't worry too much about drawing the phasor diagrams. Nobody can ask you. In this case, again, we have x axis, y axis. So phase A, regardless of the voltage type, is always on the reference level, 0 degree reference. That's our reference point. Or phase A is on x-axis, 0 degree. So VA is equal to Vm. That's the maximum voltage or for the phase at 0 degree angle. That's on x-axis. That's your reference point. But when it comes to phase B, so this is our reference point. So we have three phases, A, B, and C. And you guys know that in a unit circle, there are 360 degrees. Okay. So if you start off with the reference point right here, and then if you go clockwise, so you go this direction. So since we are going down, the angle difference between A and B is going to be 120 degrees. Now remember, we have three phases. The difference between A and B is 120 degrees. The difference between this one is C. So the difference between phase B and phase C is 120 degrees, and the difference between phase C and phase A is 120 degrees. So that's what is happening, 120 degrees right here. And if I go from this point to that one, this point to that one, that's 120 degrees. And when you go back down here, that's 120 degrees. So it's basically 360 degrees in a circle. So that's what is happening. So in other words, three phases cover the entire circle. They cover the entire circle. So phase A stays on 0 degrees. Okay, phase A stays on 0 degrees, and then of course we have to go somewhere up or down. So when it comes to phase B goes this way because we are moving in clockwise direction, and that's going this way. So that's 120 degrees. Between B and C, so we are still moving up 120 degrees, and from C to A is another 120 degrees, altogether 360 degrees. But since we are going down, we are below now, the angle for phase B is negative 120 degrees. It basically tells us that you are in a negative direction. Okay, and then you go back up, same thing. And then if you compare the phases between phase A, an angle between phase A and phase C, that's a plus 120 degrees because you go up. But in your case, you complete the circle 360 degrees. Now, voltage drop for three phase starts off with square root 3. It does not start off with 3 times. The way up here, it starts off with 2 times because we have hot and neutral conductors. But in this case, it's square root 3. The reason is that we are talking about phasor diagrams, angular difference between those three. Okay. Do you have to know everything? Not really, but if you look at these phasor diagrams, just remember one thing. I just wanted to show you that the reason we use square root 3 is because of these angular measurements, angular difference. Other than that, as an electrician, nobody's going to ask you to draw the phasor diagram, but if you want to understand electricity or the difference between single phase and three phase, and if you really want to know where the square root 3 is coming from, then yes, you have to know this one. Just as long as you remember, in a three phase, the difference, the angular difference between A and B is 120. The angular difference between B and C is 120. The angular difference between C and A is 120. So basically what you do, you complete the entire circle. So again, so phase A is right here on your reference point. So if you move down 120 degrees, then it becomes your phase B. Then you keep moving on that circle and you go 120 degrees up, and that's going to be your phase C. And from there you come back and complete the circle, and then it's your phase A. So it's just like a clock. So you start off with 3 o'clock level, and then you pass 9 o'clock, and somewhere in between is going to be past 6 o'clock, and somewhere between 6 and 9 you will have phase B, and then you again pass 9, and somewhere between 9 and 12 you're going to have phase C, and then you pass 12 and go back to 3, and that's phase A. So basically that's how it is working right now. So there are 360 degrees in one cycle. Okay, so hopefully you understood that part. Just remember, when you are doing the voltage drop and you look at the voltage drop 2 times, 2 conductors, 2 wires, round trip, square root 3, not 3, because of the angular difference. Okay, so I'm going to pause and start off with other topic. All right, let's continue on with the 3-phase circuit configurations. So what I did, actually, I put one of the 3-phase configurations, as I stated earlier, and you may remember from AC/DC class that when it comes to 3-phase circuits, you have 2 main configurations. One of them is called 3-phase delta. It looks like a triangle, and the other one is star or Y configuration. So in this case, this one is 3-phase delta. I am going to actually discuss this one. Then I have 2 more items for another slide. Is delta high lag, and then star connection, because we can make some changes to this one. So we got a triangular shape configuration, also known as 3-phase delta config. This one does not contain a neutral, so we have 3-wire or 3-phase delta configuration. So we got phase A right here. I drew different colors. This is phase A. So we have 3 different windings. So this is one of those windings. This is another winding, and that's another winding. So we got 3 different windings, but this is pretty common config that you are going to see. So 3 windings are linked together. There's a loop. So the voltage across each winding is called phase voltage. So we get a phase voltage right here. We get a phase voltage right here. We get a phase voltage right here. Okay, this one is listed as balanced delta because all of these voltages are the same. Okay, so primarily this one is used in commercial and industrial applications, especially 3-phase motors, power distribution systems, so on and so forth. So, and of course no neutral. This one, when it comes to a delta connection, since there is no neutral, if we lose anything, and since there is no neutral, if any device doesn't need neutral, we'll be able to use delta configuration. Okay, highly reliable, because if one of those primary windings, again, when it comes to configuration, we can have delta to delta connection, we can have delta to Y connection, we can have Y to delta, Y to Y, so on and so forth. Again, it depends what we're trying to get at. Okay. So again, this one is very reliable. If one of the primary windings fails, the secondary is still able to produce voltage on all three phases. So even though if we use one of these windings, one of the coils, okay, we will still be able to produce voltage on all three windings on the secondary side. Okay, the only requirement is that the remaining two windings that are still intact, they should be able to drive the load. So again, application is commercial and industrial. You are not going to see this type of config in residential property. But as you guys move up in code D and motors, and I think they will review this one more time. So just go over your Article 310, and if you have a delta connection, or read up on these, or watch these videos, and you should be able to understand what's going on, because you need this one for commercial and industrial applications. Okay. So as an electrician, you have to know what it is, how to make the connections. If you have to connect a motor using somehow delta configuration or three-phase circuits, this is where you are going to see them. Any device that doesn't need neutral, this is good for those applications. Or devices that need constant voltage, so you have motors that require 240 volts, then definitely this is good. Balanced load, voltages are the same. We cannot have different voltages. If you get different voltages, then we get unbalanced system here. Now, the only thing that you have to know when it comes to finding the voltages, so the voltages, remember, this is your phase voltage across this winding, but the voltage between these two lines is also across the phase. The voltage between these two lines and phases is also across this winding. The voltage between these two lines, between A and C, is also across this terminal. So in this case, what happens? I wrote up here. This is the equation. You can write on page 689 of your textbook. So phase voltage VPH is equal to V line. Okay, phase voltage VPH equal to V line, which is also equal to VAB, VBC, and VAC. So VAB is the voltage between line A and line B, or phase A and phase B. VBC is the voltage between phase B and phase C, and VAC is the voltage between phase A and C. So AB, BC, AC, they are the line voltages between 2 points. There is no neutral here. So line to line or line voltage. Again, some people call it line to line voltage between this line and that line, which is the same as across this terminal. So if I give you a voltage across any of these 2 points, or any of these 2 points, or any of these 2 points, the same voltage is going to appear across all of them in a balanced system. So the phase voltage, which is across an individual winding, so remember I can drag this up here. So this is your phase. If this is 240 volt, which is like this, they're all connected together. They're right here, 2 points connected right here, 2 points connected right here, 2 points connected right here. So you get 240 across here. So they're across, so you get the same voltage, 240 between these 2 points, because you have point up here, point down here. Okay, so 240, 240, 240. So just keep this in mind. In a delta or in a triangle, because it looks like a triangle, the voltages are the same in a balanced system. So VPH is 240 across all of them. Let's work on another example over here. So let's say I'm going to ask you this question, let you think. For if this voltage is equal to 480 volts, if the voltage between point B or phase B, so this is phase B right here, this is phase C, if the voltage between these 2 points is 480 volts, how much is the voltage across this point? See, if this is 480, how much is across this? Exactly same thing, 480 volts. How much is the voltage across these 2 points? 480 volts. So once you are given a phase voltage across any one of these 3 phases, you can determine the voltage across other 2 phases. So in this triangular shape, okay, so where there is no neutral, because later on we are going to introduce neutral, and there is no neutral, the voltages across each phase are equal, and the same voltage appears across these 2 terminals. You know, if this is A, this is C, that's where these points are. That's the point A. This is point A, okay, and of course the voltage, you can call it VAC or VCA. If this is 240 volt, let's call it V phase. V phase is the same as winding voltage, voltage across a single winding. So this is one of the transformers here. This is one of the windings. That's called phase voltage, 240. How much is between these 2 points? You know, phase is right across from that terminal. VAC, 240. Okay. Same thing happens over here. So this is, so this is one point, that's point B, that's point C. If I give you this voltage, any voltage, it can go up to 600 or 2000 volts again, that's my phase, or also now phase voltage is across this winding. Phase voltage is the same as winding voltage. Okay. Well, in this case, this is VBC or VCB, doesn't matter how you use it, that is also equal to 500 volts. So in summary, just remember, in a delta, you get 3 windings. You have windings like this. So you got this and you got this. So if the voltage across any of these legs is given to you guys, you can easily determine the voltage across that one and across this guy, because they're all the same in a balanced system. Okay. So again, this is one winding, that's another winding, that's another winding. Look at 3 different windings. They're connected at 2 points. 2 points right here, 2 points right here, 2 points right here. So one more thing here. So if I give you that value, and let's see if we can determine. So this is 600 volts. Okay, so that's a 600 volts. If the voltage between these 2 points is 600, how much is across these 2 lines? So let's make it 600 here. So what I did, I gave you 600 volts across this winding. Well, if I call this one point A, because this is where point A is, and this is point C, so that's VAC. If this is 600 volts, how much is across this? Because these, you take the meter, just remember, when you place the meter across these 2 points, you are indirectly or directly placing meter across that winding, 600 volts. So I'm assuming you guys understood what I just did. So again, the voltage across this point is the same as the voltage across these 2 points, is the same as across these 2 points, which is basically, remember here, when you are placing a voltmeter, let's place a voltmeter right here. That's your voltmeter. Okay, so you are placing a voltmeter between these 2 points, and somehow I say I have 600 across that link or coil. How much is across that one? Exactly 600 volts, because the voltage across this one is 600 volts. Voltage across this one is between these 2 points, 600 volts, and so on and so forth. Okay. So I'm hoping that you understood that part. So pretty straightforward. Just remember this equation. I'm going to write this equation for you one more time. So V phase is the same as V winding. Okay. P HASE is the same as VAB, is the same as VBC, is equal to VAC. So they're all equal. So phase voltage right here is also known as winding voltage, known as AB or line, BC or line, and AC or line. And if you guys have any questions, please shoot me an email. Thank you, and I'll see you later.